today's lecture, which is about the three-phase induction motor. So this is the structure, in this picture, the structure of the three-phase induction motor. And this is a small size three-phase induction motor. And for your information, the vast majorities of the electrical motors are based on induction motors. So I would say like 75% of the motors are induction. It can be either three-phase, single-phase, whatever, but it's based on induction. The advantages of induction motor is we have the capability in controlling the speed, while in the synchronous, it works only on constant speed application or constant frequency application. That was in the old science, but after the inventing of the power electronics, now we can control the speed of any of the induction or the synchronous without any problems. But in old science, before the invention of the electronics, the induction was the only motor that we can control the speed. Then, for the induction and the synchronous, most likely the induction has lower efficiency than the synchronous. So the synchronous has the highest efficiency. That's why we see in the modern EVs, they are based on synchronous, not induction. Because now we can control the speed of the synchronous, and the synchronous, especially like permanent magnet synchronous motor or brushless DC motor, those are special type of three-phase induction synchronous motor. These motors, lighter size, lighter weight, and provide good efficiency or high efficiency with smaller size. So they have more advantages, so this make them applicable in like EVs as an example. Okay, so here is the construction or the overall like three-phase induction motor. You can see there are many things like cooling fans, rotor, stator, terminal box, the bearings, the shafts, etc. So there are many things. So, but in here we will model this into an equivalent circuit. So we will not take into consideration many factors like cooling fan. We will not put it in our consideration. We just mainly focus on the electrical part or the most important part in how to run this motor. So again, keep in mind when we model the motors, like especially like in the generators, induction or synchronous generators, and here the motor, it's not 100% the overall model. It is just like they call it the steady state model, and it is a very special case, but it works and it's proved its efficiency, especially on our perspectives, which is assuming everything working fine. Assuming it's steady state, assuming, for example, the cooling fans working well, the other thing, the bearings are well, we don't need to do any other maintenance. So we will assume everything working well. Then here is in how to run that motor or how to run that generator. Okay, so the induction, the difference between the induction and the synchronous, regarding to the stator, they are the same. So the stator is identical to the synchronous. There is no problem with that. But what's the difference between the induction and the synchronous is the rotor. So the rotor is different. We can say in the structure is similar, but we used to say in the... Okay, why the pin is not working? Just pardon me, I need to... So in the rotor of the synchronous, we used to say it's based on a magnets. 2-pole, 4th pole, north pole, south pole, etc. But here, it is not magnets. So basically, there will be, for the rotor, it will be based on coils. You will see some coils. Coils that are shorted together. This means we don't have a magnets, so there is no magnetic field. Okay? There is no magnet in the structure. There is coils, and these coils are shorted together. This means we don't have a magnets. Okay. So we need a magnetic field to run the motor, right? According to Faraday's law, we need to have a magnetic field. We need to have electrical currents, then we'll produce a moving or we'll produce a rotation. Here, we didn't have. Okay, so what should I do? So there will be something that creates the magnetic field, which will not be based on the magnets, but there will be some coils and currents turns on coils. Then this will produce a magnetic field, according to physics. You can recall physics and magnetics. So here again, the rotor is different. This makes rotor speed different than stator speed. In synchronous, rotor and stator, we used to say they are the same speed. We didn't worry about. We didn't say rotor speed, stator speed. We used to say rotor speed and that's it. Here, since the rotor structure is different, it will be two different speeds. Rotor speed and stator speed. Or in other words, actual speed, which is the rotor speed, stator speed is the mechanical speed. So we can say there are some differences. Or we call it sometimes synchronous speed. So I would say the rotor or the stator is very similar to the synchronous. We will call it synchronous speed, the stator. While the rotor, it's different, so it will be called rotor speed. So we will have two different speeds. Anyway, here is how the structure looks like. So there are coils and shorted together. Since coils shorted together and there is a current, electrical current flowing, this will produce a magnetic field. According to the magnetics, this will be North Pole, this will be South Pole. So the magnetic field will be produced because of the inside the rotor, but this will happen not because of a magnet. This happens because there is a shorted and there is electrical current flowing there. So again, this yields to be rotor speed does not equal to stator speed. So stator speed, in other words, we will call it as synchronous speed, which is omega s or ns. Rotor speed, this is the actual speed, which we will call it omega r nr. Recall in synchronous, we used to say omega s, omega r the same, while here they will be different. So I would say in synchronous motor or generator, whatever, omega r equal to omega s, nr equal to ns. Because the stator and the rotor, they are following each other or the same. But here, I mean, the difference, which is on the stator, different than the rotor. So, I mean, the rotor here is different than what we have in the synchronous. Then this yields to be different speeds. And here is the point. Since synchronous speed is every time fixed, while rotor speed is something changing, that's how we do the change. So in summary, we have 3 coils, because 3-phase, 3 coils. Then, when omega r does not equal to omega s, which is the rotor does not equal to the stator, or in other words, the rotor does not equal to the synchronous. So 3-phase voltages are induced in coils because they were basically the coils, as I showed you, shorted. These coils are shorted. And there will be current flowing through the coils. Then according to the magnetics, since there is current flowing through the coils, this will produce a magnetic field. When there is any current going through the coils, and when it's going in a spiral shape, you can, like the right thumb rule. The current, the North Pole will be up, the South Pole will be down. Then this makes the magnetic field. Now, since we have a magnetic field, so the interaction between the stator and the rotor, we have a magnetic field, we have electrical currents. According to Faraday's law, this will produce a moving. Then the rotor will start rotate, which will spin the rotor. And here we will have 2 speeds, which is rotor, stator, or synchronous. Synchronous speed is the same speed that we know in synchronous, or the rotor speed the same as we know in synchronous. 2 pi times f times number of poles over 2, or 2 number of poles over 2 times electrical speed, something like that. While the rotor speed, there will be difference. Okay, now since we have two different speeds, there will be a relationship between these speeds. There is something we call it motor slip. Motor slip is describing the velocity or the difference between stator and the rotor. So omega stator or synchronous minus omega rotor over omega stator. Here is in radian per second. If we now use RPM, it will be ns minus nr divided by ns. So it's like the ratio between the difference of synchronous and rotor divided by the synchronous. So we can say that the S is called slip. Then S will be, I can say like N rotor, or we can say, if we want to do the multiplication, omega S minus omega R equal to S omega S. Then we will say omega R equal to omega R here, so it will be omega S 1 plus S. So we can say we can control the speed of the induction motor by controlling the slip. S is the slip. So that's one way of controlling the speed of the induction motor. It's called slip control. So basically by changing S, I think it will be 1 minus S. Yeah, 1 minus S, I apologize, not 1 plus S. 1 minus S. By changing S, you can change the speed, the rotor speed. That's how, for example, this is the overall principle in how we can control the rotor. The rotor speed does not necessarily to equal omega S. It can be omega S or less than that. So it can be changing. So 1 minus S. So the highest velocity that it can reach when omega R equal to omega S, which is the highest velocity when it's reached the synchronous speed. While I can reduce it lower than that. So if, for example, the motor is designed to work on 18,000 RPM, or say 1800 RPM, the maximum speed that can reach is the 1800, and I can control it lower than that. Okay? So the slip S can be varying between 0 to 1. This is the slip. So if the slip is 0, this means omega rotor, look at this equation. If the slip is 0, omega rotor will equal to omega stator. Omega rotor equal to omega stator, which is the maximum speed. The max speed, something like that, you can say, for the motor. And it works at, we call it synchronous speed mode. It's now, the induction works as synchronous. So we can say, when omega R equal to omega S, now the induction motor can be considered as a synchronous working principle. Very similar to the synchronous. Now, if S equal to 1, according to this equation, 1 minus 1 will be 0, 0 times omega S is 0, so omega R will be 0. This means it's not spinning, or in other words, we call it stalled. Okay? So since it is a ratio, the slip must be between 0 to 1. But there is a question, which is, can the slip be negative? The question, yes, it can be. If it is negative, this yields to be omega R larger than omega S. Okay, this means omega R larger than omega S, which is omega S minus omega R over omega S. Since omega S minus omega R less than 0, this means this one less than 0. As a result, S will be less than 0. So this happens when rotor speed larger than synchronous speed. Okay, what does this mean? This means it is no longer motor, it will be generator mode. Okay, why? What's the point? The point, the maximum speed is the synchronous. Okay? Now, the motor is not capable to run faster than that speed. Okay, if we find for a reason it's reached that speed, then it will work as a generator. How? You can, again, imagine that you are driving a car, like you are reached the maximum speed, but suddenly your speed is higher than the desired. Or when you, for example, when you cruise control or something like that, and the old cruise control, not adaptive, which does not change the speed. Just like the cruise control, when you make 70 miles per hour, when you go down like down the hill, it will be more than 70 miles per hour, right? It will, I mean, the car in old cars cannot adjust, it cannot go back to the 70 because you are going down. It will just increase or control the fuel. It cannot control the brakes. So this means there's something pushing you, right? If you adjust your speed at 70 miles per hour, but you realize the speed is now 80 or 90, which is higher than the desired, this means there's something pushing you. It can be either someone pushing you, or it can be you are going down the hill, which is the gravity pushing you. So in this situation, we will say the motor will no longer be a motor. In order to overcome this situation, it will be as a generator. So we need to go back to the original, which is 70 miles per hour. That means when which is the rotor speed larger than the synchronous, if and only if we are in motor, in generator. While if you are in motor, you are climbing the hill, so your desired speed to reach 70 miles per hour. You don't want to go beyond than that or larger than that. So that's how we can imagine it, which is basically we don't want to go exceed that speed, which is the synchronous. So it's been designed to work as a motor for the synchronous speed, or the larger speed, which is at a synchronous speed. While the rotor speed, again, can be varying. And the maximum, that's the maximum value to work as motor. If it is larger than that, this means there is someone help you in this, which is, it's no longer a motor, now it's a generator because we need to go back to the origin. Okay, any question? Now, here is the equivalent circuit model for the circuit. So basically, this is the three-phase motor. We will convert this into an equivalent circuit, so this yields to this one. So we can see that there is R1, JX1, this is related to the stator. We have JX2, R2 over S, this is related to the rotor. Then we have JXM, this is related to the core. Okay? So this is the equivalent circuit. So R1, stator resistance, X1, rotor reactance, R2, reflected rotor resistance, X2, reflected rotor leakage reactance, then XM, magnetization reactance. All of them by taking phase A as an equivalent circuit, by converting, after converting three-phase to single-phase, because we'll assume it is balanced three-phase system. Because it's balanced, that's why we take per phase equivalent circuit. So I'm not gonna draw it 3 times. So we know that from the three-phase analysis, if it is balanced, we will convert three-phase to single-phase. In the synchronous, we used to neglect R1, R2. Neglect R1 for the resistance. In the synchronous, we used to say just JX. But here, we will not do that. R2 is dominating, R1 is dominating, so we cannot neglect any of those. So you need to keep this in mind. However, JXM, we can make some assumptions. If JXM larger than 10 times of X1 or 10 times of X2, then it can be neglected. So you can erase it from the circuits. How? So you can draw the circuit like R1, JX1, JX2, R2 over S. So you can see R2 bar, R1 bar, or JX1 bar. This is related, or we call it reflected, because basically there used to be a number of turns, then we refer this from secondary side to the primary side. This is something, you don't need to worry about it. So if you write it as R2 bar or R2, for this course it's fine. If you write it as JX2 bar or JX2, there's no problem with that. So don't worry about the bar here. Okay, but anyway, they were reflected, they were in the secondary side, but then they've been referred to the primary side. So with this situation, when we assume JXM is a very large value, then it can be neglected. So here is plus minus VAN, here is IA. So every time we will assume JXM is neglected. That's what we will do. Assume JXM is very large, then neglected. And it will be given in the values. So anyway, every time we will assume JXM is neglected. So we can simplify the circuit, so we will not go to 2 loops, then we will have single loop. And in order to calculate the current for single loop, V over the sum of impedances. That's it. Okay? So this will make the circuit more simple. So that's the equivalent model, circuit model for the induction, again, after converting three-phase to single phase, after removing JXM effects. So this is, again, a very special case, but it is decent model. I mean, it can be good and applicable. Now, let's go to worksheets number 15. This is the last worksheet in this course. So worksheet number 15, induction motor. Now, since I said that we have synchronous speed, we have rotor speed, right? So we have two speeds. And don't forget the electrical speed that we already have before. And when we discuss the synchronous, we used to say we have two speeds, synchronous and electrical speed, or electrical and mechanical. And we said the mechanical is the same as the synchronous, right? That was before, the same as the synchronous, the same as the rotor. Now, we still have electrical speed, but the synchronous speed or the mechanical speed can be divided into two things, which is rotor speed, stator speed. Stator speed will be called as synchronous speed. Rotor speed will be called as rotor speed, as is. Because the rotor speed is the actual speed. What's the actual speed? Is it the synchronous? No, it's the rotor speed. Before, again, in the previous, when we discussed the three-phase synchronous motor or generator, rotor speed and synchronous speed, we used to say the same. We didn't talk a lot about it because they are the same. Now they are different. That's the point. So we have here electrical speed. So NE, which is N in RPM, omega in radian per second. So NE F times 60 with electrical, 2 pi times F, 60. That was electrical speed. Mechanical speed, or the synchronous speed, NS equal 2 over number of poles times NE. Then the same, omega S equal 2 times number of poles times omega E. And the famous formula 120 F over number of poles, that's the synchronous speed. Now, we have the third speed, which is the rotor speed, NR omega R. NR 1 minus S times NS, omega R 1 minus S times omega S. So again, here, keep in mind, and when we discuss the synchronous, we used to say omega R equal to omega S. But in induction, they are no longer, induction, yeah, they are no longer equal to each other. Okay? That's why we have the slip definition. Does this make sense? So it's very important to distinguish that we have three different speeds. All of them are virtual. The only actual speed is their rotor. Okay? Synchronous speed is something virtual, that's what's supposed to be, that's the maximum speed. Electrical speed, that's regarding the number of poles, that's how the electrical field speed will be, or the electrical flux will be. So whatever, that's what's supposed to be without including the number of poles. Then the last one, which is the synchronous, or the rotor speed, which is the one that we will use. Again, this is the equivalent circuits again. So the point is, or the things that we have in this circuits, R1 and R2 cannot be neglected. Since we have R1 and R2, this means we have resistors cannot be neglected. And wherever we see resistors, there will be losses. So the electrical engineers, we don't like losses as an electrical engineer. We don't like resistors. Whenever we see the symbol of resistors, this means there will be losses. And these losses will go as what? Heats. Resistors losses goes as heats. And this is something that we don't want. But it exists. I cannot remove it. So we need to keep in mind that there will be losses. Recall, in the synchronous, these resistors can be neglected. So we didn't discuss a lot about the losses. The only losses that there were in the synchronous are the rotational losses. Or in other words, we call it mechanical losses because of the rotational. Rotation is the mechanical losses. Now we have resistors. So far, we will have two types of losses. We will have electrical losses because of the resistors, mechanical losses because of the rotational losses. Okay? So since we have a three-phase, we can find V line to line, because basically the value given V line to line, then V line to neutral, V line to line over root of 3, then VAN will equal V line to neutral angle 0. I think we have done this more than 100 times, so you should be familiar with this. Then for the losses, again, we have mechanical losses, electrical losses. Mechanical losses because of the rotational losses, so we know the torque, K times omega R. Then in order to convert the torque to power, which is torque rotational losses times omega R. So now we have power losses regarding to the rotational losses. Again, this is mechanical. Then we have electrical. Electrical, we have two R's. We have the stator, R1, R2 for the rotor. So we will have something called stator winding losses, or as a shortcut SWL, which is 3 times I squared times R1. Then we have rotor winding losses RWL, 3 times I squared times R2. Keep in mind, when you substitute I, is there any bar above this? No bar. Therefore, substitute only the magnitude. Don't put the angle. And this is real power. So there is no way to have an angle or to have a complex expression for SWL or RWL, because all of them are real powers. So it's very important to substitute only the magnitudes. Don't substitute the angles. And why we have 3? Can anybody tell me why we have 3? 3-phase, exactly. So it's I squared times R. We know I squared times R. This is the power of the losses of the resistors. And again, when you substitute only the magnitude. And there is 3 because it's 3-phase. Because this is the per phase equivalent circuit for phase 1. Then when phase 2, phase 3, this will be different. And most likely XM, again, we will assume a very large, then we can neglect this. As a result, the sum of the losses will be stator winding losses, rotor winding losses, plus rotational losses. Or in other words, electrical losses plus mechanical losses. Okay? Rotor winding or mechanical losses, which is the rotor losses, this will basically torque times omega R. Then torque is K omega R, then it will be K times omega R square. Then rotational winding losses, or SWL, RWL, will be 3 times I square R. It's R1 or R2, depending on if you are stator, R1, rotor, R2. Okay, any question? Now my target is to calculate the efficiency, the same thing that we used to do it before. Efficiency, P out over Pn. So it can be as P out over P out plus losses, or it can be Pn minus losses over Pn, such that we can say P out equal Pn plus or minus losses. That's how we can find them. So whatever more convenient for you, you can calculate the losses, calculate Pn, then you can calculate the efficiency. You can calculate the losses, calculate P out, then calculate the efficiency. Or you can calculate Pn, P out, whatever you want. So you have 3 ways to do it. 3 ways, 3 different formats. Now again, the losses is the sum of stator winding plus rotor winding plus rotational losses. Pn is very similar to what we know in the synchronous, because that's the synchronous stator, the induction stator, the same as the synchronous stator. So it will be 3 VAN IA cosine alpha minus beta. We know this one. And again, 3 because it's 3-phase. Then P out here, it is P dev minus P rotational losses. It's also very similar to the synchronous, right? Development power minus rotational losses. But the thing that we have, P dev is different. P dev equal 3 I squared 1 minus S over S times R2. So this is different than synchronous. P dev in synchronous, or development power in the synchronous, I think it was 3 EF VAN over XD sine delta. Here, it's 3 I squared 1 minus S over S times R2. Okay? You need to keep this in mind. So what I encourage you when you write your note sheets, write the formulas of induction alone, like try to split the sheets. So here is the formula of induction alone. Here's are the formula of the synchronous alone. So I don't want you to get confused between them. I don't want you to use the P dev of the synchronous on the induction, then you will get lost. So where is delta? There is no back EMF here, electromotive force here. It's the circuits, there is no source, voltage source, EMF. It's only based on the resistor. So you need to keep this in mind. Then the important formula, P dev, again, T dev times omega r, we know this. The rotational T dev equal TRL plus T load, we already know this before, the same as the synchronous. Torque power characteristic, the same as the synchronous. Then here's the charts, like summarizes how the power flow will go. So you can see that here is Pn going inside the motor. This box is the motor. So here is the input power, which is the electrical part, input power. The mechanical is torque over rotor, speed of the rotor. Then, the first thing when the electrical current will go, it will start the stator, right? It will go through the coils of the stator. So there will be subtract the stator winding losses. After that, it will go, the energy flow or the power flow will go to the rotor. Then there will be rotor winding losses. Now we are done with the electrical parts. The motor starts rotating. Then we will see we are in the mechanical parts. Then there will be subtracts the rotational losses. After that, it will be the output, which is P out. Okay? So the development power is basically most likely located here, P diff, before the rotational losses. Output power is located here. Input power is located here. So you need to keep in mind the development power is the input power minus electrical losses, which is stator winding and rotor winding. It's not, you don't need to subtract the rotational losses, because rotational losses, this will be regarding to the mechanical parts, while the development power is basically associated of what's happening after the end of the electrical parts without including the mechanical. Okay? So development power only for the mechanical, electrical parts. While the output power is related to what's going on after removing the losses, after the mechanical parts. Okay? So this flow chart can summarize everything, and even like the formulas that I wrote here, these are very important for you. So I encourage you to keep or to write those first to understand them very well, then write your summary in your note sheets. Any questions about this worksheet? Okay, now we need to go to the example. This is cumulative example. So in this example, we need to calculate the efficiency, and we have many things to do. So every time, whenever we deal with the synchronous or the motor, the first thing that you need to do is draw the equivalent circuits. Okay? So you need to keep this written in your note sheet. Draw the equivalent circuit, and we already know the equivalent circuit. So you have two equivalent circuits before removing JXM and after removing JXM. Whatever more convenient for you, you can write it. But keep in mind, when we do the analysis, you need to remove JXM, assuming JXM is very large value. So here, look at the question, 460 volts, 100 horsepower. Again, we are using horsepower for the motors, volt ampere for the generators. But here it's horsepower. 3-phase, 4-pole induction motor operates, look for where it's operating. It operates at the rated voltage. And we given the frequency 60 hertz. Running 1770 RPM. So this is the actual speed, because it's running at this speed, or in other words, rotor speed. And we have the following information: R1, JX1, X1, JXM, R2, etc. So we can look at XM and X1. 10 times X1 will be 1.9, XM 7.4. So basically, XM is way larger than X1, way larger than X2. Therefore, it can be neglected. So the question says we need to find the slip, all currents, all powers, torques, power factor of the source, and efficiency. So we need to do everything. So the first thing, when we do our analysis, try to write the values on the equivalent circuits. So let's write the values on the equivalent circuit, and we can need to find the unknowns. So we have R2, R1 is given as 0.04232. JX1 is J0.190, I think 19044. 19044. JX2, J0.19044. JXM equals J 7.4, what is 406. R2 0.04232. Keep in mind it's divided by S. I didn't know S yet, so I'm gonna keep it as divided by S. Now in this circuit, the only thing that we don't know here, VAN. So let's try to do VAN. Given this question, V line to line equal 460. Therefore, V line to neutral equal 460 divided by root of 3, which is 265.58. As a result, VAN bar will be V line to neutral, which is 265.58, angle 0 degrees. Now, we know VAN. The other thing that we can do some simplification, this is very large, then it can be neglected. So I'm going to redraw the circuits. Here is I, A, then here is R1, JX1, JX2, R2 over S, then here is plus minus VAN. Then now we know all of the values here, 0.04232 divided by S, here J 0.19044, J 0.19044, 0.04232, then here 265.58 angle 0 degrees. So in this circuit, the only unknown, S, I need to know S. Then after that, I can calculate IA. So let's calculate S. S, which is the slip, equal to NS minus NR over NS, or omega S minus NR over omega S. For this question, NR given as 1770 RPM. Do we know NS? No, we don't. What should I do? You need to calculate it. How to calculate NS? Go to the worksheets. Calculating NS, basically you need to calculate the electrical speed, which is 60 times F. Then you can say NS, it will be as number of poles, 2 over number of poles, or actually let me say an electrical times number of poles over 2, or 2 over number of poles, I think 2 over number of poles, times 2 over number of poles. Or in other words, we can say NS 120F over number of poles, whatever. Do we know number of poles? Yes, given in this question, number of poles equal to 4, frequency equal to 60 Hertz. So we can plug this here. Then NS will be 120F, 120 times 60 over number of poles 4, so it will be 1800 RPM. Now I'm ready to calculate S, which is S equal to 1800 minus 1770 divided by 1800. So S will be 0.017. Then I can plug this in S. Now I know S. 0.04232 divided by 0.017. Okay? Does this make sense? After calculating S, the other thing that I need to do, which is basically to calculate the currents. So I need to calculate everything in this circuit. How can I calculate the currents? Look at this circuit. How can I calculate the currents? It is single phase AC circuit problem. Chapter 5. How can I calculate I? You can see this course is cumulative, so that's why we have learned DC, AC, power, because we are applying everything here. So you have this circuits. How can I calculate the currents?
Find Z equivalent and then do Ohm's law.
Exactly. Find Z equivalent, do Ohm's law. That's one way. Other way, KVL. Whatever. It's single loop, or you can say it's single loop. So I would say, it is single loop. So IA will be VAN over the sum of Z, right? So it will be as VAN divided by sum of Z, which is R1 plus JX1 plus JX2 plus R2 over S. Keep in mind, it's plus R2 over S. Then let's substitute the values. VAN equals to what? 265.58 angle 0 divided by 0.04232 plus J 0.19044 plus J 0.19044 plus R2, which is, okay, I have space here, 0.04232 divided by 0.017. 0.017, yes. Then the answer will be, after like this in the calculator, I think it will be around 108.88 angle negative 26.32 degrees amperes. I'm not exactly sure about this number, but I'm gonna assume it like this way. So now I calculated the currents. Let me just read the question to make sure what else do we need to calculate. So we need to calculate all slips, currents. Now we need to calculate all of the powers. P in, P out, stator winding losses, rotor winding losses, etc. So let's calculate the losses first. As we know, for the losses, we have stator winding losses. So stator winding losses, 3 times I squared times R2 bar. So 3 times I squared, we already calculated as 108.88 square. Don't substitute the angle. There is no bars here. Don't substitute angle negative 26. This is one of the common mistakes. Times R2, which is 0.04 times R1. This is stator winding losses. Times R1, 0.04232. So it will be, I think, 1291 watts, something like that. I think, no, not this one. It will be 1505 watts. Then we have rotor winding losses, 3 times I squared times R2, which is 3 times 108.88 squared times 0.04232. Keep in mind here it's times R2, not R2 over S. That's the formula. So it will be the same, 1505 watts. So we just calculated all of the stator losses. Now let's calculate, all of the electrical losses. Let's calculate the mechanical losses. So given in the question, torque rotational losses equal 0.06299 times omega r. And we know the power rotational losses equals to torque rotational losses times omega r. As a result, this yields to be 0.06299 times omega r squared, because I need to calculate the power, not the torque. Now, what should I do? What should I substitute omega r? Okay, wait a minute. We have nr, not omega r. Given nr as 1770 RPM. How about omega r? We know the speed. We need to convert this in different units. So recall the conversion between radian per second and RPM. Omega r equal to nr times 2 pi over 60. Okay? So this yields to be 185.35 radian per second. Keep in mind, whenever you see omega, radian per second. Whenever you see n, RPM. So keep in mind, you need to convert this to radian per second. So it will be 185.35. So as a result, the power rotational losses will be 0.06299 times 185.35 square. Then the answer will be 2,164 watts. As a result, in order to calculate the losses, the sum of the losses will be stator winding losses plus rotor winding losses plus rotational losses. So the sum will be around 4,959 watts, something like that. Okay? Then we need to calculate all of the powers. So how about PDEF? PDEF equals 3 IA square 1 minus S over S times R2 bar. So it will be 3 times 108.88 It is 108.88. 108.88 square times 1 minus 0.017 over 0.017. It's just like plug the formulas. Times 0.04232. So P div after plug these numbers will be 74.86 times 10 power 3 watts. Then, in order to calculate the output power, it is P div minus P rotational losses, which is 74.86 times 10 power 3 minus 2.164 times 10 power 3, because we already calculated the rotational losses. So the answer will be 72.7 times 10 power 3 watts, or in other words, 72.7 kilowatts. That's P out. The other thing that we need to do, which is calculating Pn. Pn equals to 3 times VAN times IA cosine alpha minus beta, which is going to be, substitute the numbers, 3 times 265.58. Keep in mind, there is no bars above these numbers, so substitute only the magnitudes. So it's times 108.88. Cosine, the angle of the voltage is 0, the angle of the current negative 26.32 degrees. So Pn will be 77.76 times 10 power 3 watts, or in kilowatts will be 77.76 kilowatts. Then the last thing to calculate the efficiency, or the thing for the last thing, which is to calculate the efficiency, P out over Pn. P out, we already calculated it here as 72. This is P out, and this is Pn, so it will be 72.7 times 10 power 3 divided by 77.76 times 10 power 3. So the answer will be 0.935, or in other words, will be 93.5 degrees. That's the efficiency. Now the last thing is to calculate the power factor. So the power factor, which is the cosine of the voltage, angle of the voltage minus the angle of the currents. So which is cosine of 0 minus negative 26.32 degrees, which is going to be cosine of positive 26.32 degrees. And since it is positive, therefore it is lagging power factor, then the cosine of 26, 0.896. Okay? If we need to calculate the torques, T div, P div, here is a cumulative example. I'm going to assume we need to calculate everything. That's why it's kind of complicated. So it will be 403.9 Newton meters. Then if we need to calculate T div, will be T rotational losses, or in other words, plus torque rotational losses. Therefore, load torque will be T div minus T rotational losses. Then it will be as 392.2 Newton meter. Okay? So that's overall, which is I calculated everything. So keep in mind, it's very important for you to calculate the efficiency. You can notice here the efficiency is 93% or 0.935. If you realize the efficiency is negative, definitely there's something wrong in your calculation. If you realize that efficiency is a complex number, then definitely you substituted the angles and when you calculate the power. So keep in mind, check your calculations. The efficiency must be positive, must be between 0 to 1. Don't calculate the efficiency as 1,100%, 1,100. So when you do your calculation in the quizzes or exams, so if you realize the efficiency larger than 100%, don't write it. Or when you write it, when you box your answer, you need to say there is something wrong. Other than that, you will get a negative because of this. Because as engineers, we know that efficiency cannot be a negative number, cannot be a complex number, cannot be higher than 100%. Okay? Any questions about induction? So here is the induction, the end of the induction and the end of chapter 15.